Welcome, everyone, to this deep dive. It's going to be a cool one. We're
Oh.
going to be looking at the connection between compact stars and dark matter.
All right.
And we're really lucky today. We've got an expert to talk about this. And,
Yeah.
you sent me a research paper on this topic. And
Really?
it's fascinating stuff. So let's jump right into it.
Yeah. These compact stars are very special objects. They're unique laboratories
Yeah.
in the universe.
Now, just to kind of set the stage here, we all know that white dwarfs and neutron stars
Yeah.
are what's left over after a star dies.
Right.
But what about them makes them
Well,
so important for dark matter?
it's their extreme nature. I mean, they're very, very dense.
Okay.
Like, imagine you're taking the entire mass of the sun and you're squeezing it into a sphere
Wow.
the size of a city. That's how dense neutron stars are.
Oh, wow.
And that density creates incredibly strong gravitational fields.
Okay.
So strong that they can actually accelerate dark matter particles to near the speed of light.
So these compact stars are almost like natural particle accelerators,
Exactly.
giving us this window into particle interactions that we could never replicate
Yeah.
here on Earth.
It's impossible to do that here on Earth.
Now, I remember reading about the layered structure
Right.
of neutron stars.
Yes.
Can you tell us a bit more about that and how it affects their potential?
Absolutely. As you go deeper into a neutron star, the density increases
Right.
dramatically, and that leads to some really exotic states of matter.
Huh.
You have the crust, which is layered, and you go deeper, you encounter what we call the pasta phases.
Bomba phase.
Pasta phases, yes. That's where the nuclear matter gets squeezed into shapes that resemble different types of pasta.
I love that.
Yeah.
So tell me more about this nuclear pasta and how it even forms.
Well, imagine a cosmic pressure cooker. The forces inside atomic nuclei are pushed to their limits.
Right.
The strong nuclear force that binds protons and neutrons starts to compete
Okay.
with the electromagnetic force. So
Yeah.
you get this competition, and then the immense pressure forces the nuclear matter to arrange itself in these
Wow.
weird configurations. Some regions might look like spaghetti strands,
Okay.
others like lasagna sheets or even gnocchi.
That is incredible.
It is.
So the structure of matter is fundamentally different in these extreme environments.
Right.
But how do these pasta phases affect how dark matter might interact with the star?
The different densities and compositions of these layers influence how dark matter particles scatter
Right.
off the star's matter. Some layers might be more effective at capturing dark matter,
Got it.
while others allow it to pass through more easily. So understanding the structure is really important for modeling these dark matter interactions.
So there's a lot of different factors at play here, it sounds like.
It is a complex interplay of factors.
But let's move on to the detection mechanisms.
Okay.
How can we actually observe the presence of dark matter using these compact stars?
There are a few proposed mechanisms, but the main two are kinetic heating and annihilation heating. Kinetic heating is basically a process of energy transfer through collisions.
So is it kind of like a cosmic game of billiards
Yeah, you could say that.
with dark matter as the cue ball?
As dark matter particles travel through a compact star, they collide with the star's particles.
Okay.
They transfer some of their energy. And over time, this can lead to an increase in the star's temperature.
But this heating must be incredibly faint.
It is.
How can we even detect it?
It is a big challenge, but not impossible. Sensitive infrared telescopes, like the James Webb Space Telescope, might be able to detect this excess heat.
Okay.
But as you said, it's very difficult to differentiate
Yeah.
this heating from other astrophysical processes.
We talked about accretion and pulsar emissions.
Right.
Are there other things that we need to consider?
Yeah. We also need to consider the cooling mechanisms
Okay.
of the compact stars themselves. For example, neutron stars cool down over time through neutrino emission. So understanding this cooling process is important for disentangling any potential heating effects caused by dark matter.
Okay. So it's a really complex puzzle
It is.
and requires careful observations and sophisticated modeling to really understand everything that's going on.
Absolutely.
Now, you mentioned another detection mechanism, annihilation heating.
Yes.
How does that differ from kinetic heating?
Annihilation heating relies on the possibility of self-annihilation.
Self-annihilation.
So in some dark matter models, when two dark matter particles collide,
Right.
they can annihilate each other, releasing a burst of energy.
And that energy release would be a lot stronger than the energy transfer we see with kinetic heating.
Exactly. And that makes it potentially easier to detect.
So it's easier to detect, but it's also very dependent on the specific properties of the dark matter particles.
Yes, that's right.
Okay, so each detection method has its own advantages and limitations.
Right.
Before we go into the specifics of white dwarfs and neutron stars,
Yeah.
I want to talk a little bit about the research paper that you sent.
Yep.
Can you tell us more about its focus and what are the key findings?
The paper gives a good overview of the different ways
Okay.
we can use compact stars to search for dark matter. It explores various theoretical models
Right.
and discusses the observational signatures we might expect to see.
Does it highlight any specific challenges?
It does. It emphasizes how important it is to accurately model the internal structure of compact stars,
Okay.
including those pasta phases,
Yeah.
to make reliable predictions about dark matter interactions.
Mhm.
It also stresses that we need to carefully consider
Right.
other astrophysical processes that could mimic or mask dark matter signals.
So it's calling for both theoretical and observational precision.
Yes.
Are there any results from the paper that you found particularly interesting?
The paper highlights the potential of using multi-messenger astronomy,
Okay.
combining observations from different sources like electromagnetic radiation and gravitational waves.
Interesting. So using multiple perspectives
Right.
to probe a single phenomenon.
Exactly. It could help overcome some limitations.
Yeah.
Of relying on just one type of observation.
That is fascinating.
Yeah.
Now that we have this overview,
Yeah.
I'm really excited to dive into the specifics of how white dwarfs and neutron stars can be used to study dark matter.
Okay.
So let's start with white dwarfs.
All right.
What are the unique possibilities and challenges that they offer?
White dwarfs are less dense than neutron stars, so they offer a different set of conditions
All
for
right.
studying dark matter. One interesting possibility is that dark matter could actually trigger thermonuclear explosions in these stars.
You're saying that dark matter could cause a white dwarf to go supernova.
Yes, it's a theoretical possibility.
That's amazing.
If enough dark matter accumulates in the core of a white dwarf,
Wow.
it could reach a critical mass and trigger a runaway fusion reaction,
Oh, okay.
leading to a type Ia supernova.
Could this potentially explain the observed type Ia supernovae?
It's a question worth investigating.
Yeah.
But we need to consider the complexities
Right.
of dark matter thermalization within white dwarf cores.
Thermalization. Can you explain that concept a bit more?
Thermalization is the process by which dark matter particles reach a state of thermal equilibrium
Okay.
with the star's matter. This involves energy exchange through collisions,
Hmm.
and it can affect how dark matter energy is deposited within the star.
So understanding how dark matter thermalizes
Right.
is really crucial for interpreting any potential signals that we might see.
Exactly. And this process is influenced by several factors, like the density and temperature of the white dwarf core and the properties of the dark matter particles themselves.
It sounds like we're just scratching the surface here.
We are.
White dwarfs offer unique possibilities, but they also come with their own set of challenges.
Yes.
Maybe we can dive deeper into that in our next segment.
Okay.
But for now, let's shift our focus to neutron stars.
Okay.
What kind of dark matter-related phenomena
Well-
can we expect to see from them?
Neutron stars, with their extreme densities and gravitational fields, offer a whole new level of possibilities. One of the most dramatic is the potential for dark matter to actually cause a neutron star to implode into a black hole.
Hold on, you're saying dark matter can destroy a neutron star?
Yes.
How is that even possible?
So if enough dark matter particles get captured by a neutron star, they can start to build up in the star's core.
Okay.
And under all that gravitational pressure, this concentrated dark matter could eventually collapse under its own gravity. It would form a black hole
Inside the neutron star.
right inside the neutron star.
So like a seed of darkness that grows until it consumes the entire star.
That's a great way to put it. And this black hole
Yeah.
would start to accrete matter from its surroundings, basically devouring the neutron star from the inside out.
What would we actually see if this happened?
Well, this process would release a huge amount of energy,
Okay.
mostly in the form of gamma rays. We'd see a powerful gamma ray burst.
So astronomers could actually witness a neutron star being consumed by a black hole.
They could. It's definitely possible. And even after the burst fades,
Yeah.
we might be able to detect the gravitational influence
Right.
of that new black hole.
Even though we can't see the black hole itself.
Exactly. We can infer its presence through its effects on nearby objects.
It's like a cosmic detective story,
It is.
piecing together the evidence to find this hidden black hole.
Precisely. Now, the implosion of a neutron star into a black hole is pretty dramatic.
Yeah, it is.
But there are other more subtle ways that dark matter might show itself in these stars.
Okay.
Remember we talked about dark neutrons earlier?
Yeah. I'm really interested in that idea. It sounds strange.
It is a bit strange. The idea is that regular neutrons,
Okay.
the ones that make up a big part of neutron stars, could go through a process called oscillation.
Oh.
So a neutron could spontaneously transform into a dark neutron.
A dark neutron.
Yes. It's a hypothetical particle that interacts with regular matter even more weakly than regular dark matter.
So it's like a chameleon particle. It
Yeah.
changes its identity.
Yeah, I like that analogy. And these dark neutrons, once they're formed, they'd be practically invisible to us. They wouldn't interact with the electromagnetic force, so no emitting or absorbing light. And they interact so weirdly with regular matter that they would just pass through the neutron star and escape.
So we're talking about a slow leak of neutrons
Yeah.
transforming into these dark neutrons and escaping the star's gravity.
Yes. And that gradual loss of neutrons would have a noticeable effect on the neutron star over time.
What kind of effect?
As neutrons escape, the star's mass and density would decrease.
Okay.
And that would make the star expand a little bit, and the temperature would increase.
So even though we can't see these dark neutrons,
Right.
we could potentially detect them through the changes in the neutron star.
That's the idea. This is where the coldest known pulsar, PSR J214Air3933, comes in.
Okay.
Based on what we know about neutron star cooling and dark neutron mixing, this pulsar should be heating up,
Right.
but observations haven't shown that.
So another potential anomaly.
It could be. The absence of the expected heating in this pulsar could mean that dark neutrons are forming and escaping. They could be carrying away energy and preventing that temperature rise.
It's amazing how these tiny processes within neutron stars
Yeah.
could give us clues about dark matter.
It is. We're pushing the limits of what we can detect.
For sure. But we've mostly talked about individual compact stars.
Right.
Can we learn about dark matter by studying entire populations of these objects?
Absolutely. One great example is using pulsar timing arrays,
Pulsar timing arrays.
or PTAs. They consist of multiple pulsars spread across the sky that are precisely timed. By monitoring the arrival times of the pulses from these pulsars,
Got it.
astronomers can detect tiny variations caused by passing gravitational waves.
So like a giant web with each pulsar as a sensitive node,
I like that. A very accurate analogy.
detecting ripples in space-time.
And this is where dark matter comes in. Some theories suggest that dark matter could exist as compact objects,
Like what?
small black holes or dense clumps of particles.
Okay.
If these dark matter objects are massive enough, they would create their own gravitational waves.
As they move through space.
Exactly. So by looking at the data from these pulsar timing arrays, astronomers could potentially detect the gravitational waves
Wow.
from these unseen dark matter objects.
That would reveal their presence.
Right. And their distribution throughout the galaxy.
It opens up a whole new way of exploring dark matter.
It does. It's like listening for the faint drumbeat of dark matter
I love that.
against the background noise of the universe.
It's incredible how different areas of astronomy are working together
It really is.
to help us solve this mystery.
It's a testament to the power of collaboration and the ingenuity of scientists.
It is, but with all these possibilities,
Yeah,
there are also challenges and uncertainties.
absolutely.
We've talked about some of them. Can you give us some more specific examples?
One of the biggest challenges is that these objects are just really hard to observe. Compact stars, especially neutron stars,
Right.
they're incredibly small and faint, so it's hard to detect them,
Yeah.
even with their most powerful telescopes.
So how do astronomers even find them?
We have to push our instruments to their limits, use really sophisticated data analysis techniques, and often we have to rely on indirect observations.
Indirect observations.
Like we might infer that a neutron star is there based on its gravitational influence
Okay.
on a nearby star, or by detecting X-rays from its surface.
Right. So it's a lot of detective work.
It is.
Trying to piece together these clues to find these hidden objects.
Yeah, and even when we can detect them,
Right.
getting detailed information about them, like their mass, radius, temperature,
Yeah.
that's really tough.
I bet.
It takes precise measurements, careful calibration, and we need to use complex models to account for things like interstellar dust
Makes sense.
and the effects of gravity on light.
It's amazing that we can learn anything about these objects at all.
It is. It's a testament to the ingenuity of astronomers.
For sure.
Yeah.
But we also have this other challenge of separating
Right.
potential dark matter signals from other astrophysical processes.
Yes, exactly.
Can you give us some more specific examples of that?
Accretion is a good example.
Okay.
White dwarfs and neutron stars can pull in matter from their surroundings.
Yeah.
And that can heat them up and change their brightness.
Hmm.
This accretion heating can look a lot like
Right.
the heating we might expect from dark matter.
So how do you tell the difference?
It's tricky. We also have to think about pulsars,
Okay.
these rotating neutron stars that emit beams of radiation.
Right.
Those beams can heat up the neutron star too.
I see.
And it's hard to separate those effects from any dark matter contribution.
So it's like trying to find a needle in a haystack.
Yeah.
Yeah, a very messy haystack.
And then on top of all that,
Right.
we still don't even know what dark matter is.
Exactly. That's a huge challenge.
Yeah.
We have all these theoretical models, but we don't have any definitive proof.
So we don't even know exactly what we're looking for. It makes it tough to predict what kind of signals we should expect from compact stars.
It sounds like a lot of trial and error.
It is. We try to match potential signals with our theoretical predictions, and then we refine our models as we get more data.
It must be a very humbling field.
It is. We're constantly reminded of how much we don't know.
But there's also a lot of excitement.
Oh, absolutely. The potential to solve the mystery of dark matter
Yeah.
is a huge motivator.
And we have all these new technologies coming online
That's right.
that could really help us make progress.
Yeah.
What are some of the most promising developments?
We have these next-generation telescopes, like the 30-meter telescope
Oh, sure.
and the extremely large telescope. They'll be amazing for studying compact stars.
What will they be able to do?
They'll be able to see much fainter objects, and they'll give us more detailed information.
Wow. So what about advancements in other areas?
Well, in gravitational wave astronomy,
Yeah.
we have the Laser Interferometer Space Antenna, LISA.
Okay.
That's going to be a game changer.
How so?
It'll be sensitive to a much wider range of gravitational wave frequencies. So we'll be able to detect mergers of supermassive black holes.
Wow.
And maybe even study the dark matter halos around them.
It's incredible to see how all these different fields are working together to help us understand the universe.
It's a really exciting time to be in this field.
I agree.
Yeah.
Well, thank you so much for taking us on this deep dive.
It was my pleasure.
It's been fascinating to explore the connections
Yeah.
between compact stars and dark matter.
It's a fascinating area of research.
It is. And to our listeners, keep exploring these ideas and keep asking questions. The universe is full of mysteries, and every discovery brings us closer to understanding them.